So what if we have a reaction that's been going on for a while and we don't really know where we are? We don't know if we're still in the initial stages of reactants moving into products, or if we've already kind of met that apex and now we're starting to see the reverse reaction take place, because that could be a possibility. Well, if a reaction mixture containing both reactants and products is not at equilibrium, the question becomes, how do we know which direction it will proceed? Well, there's a way to figure that out. And the answer is that if we take the current concentration ratios and compare those to the equilibrium constant, that will give us some clue of where we are in the process of the reaction. So then the question becomes, what is that current concentration ratio? Well, that's what's called the reaction quotient. And the reaction quotient is very much like the equilibrium constant, where we would take the concentration ratio of the products raised to the power of their coefficients over the reactants raised to their coefficients. But instead of calling it the equilibrium constant, we just call it the reaction quotient. So how would we actually go about putting together this reaction quotient? Well, if we had a reaction going on like this, and let's say that everybody here's a gas, that'll make it nice and easy, then the way that we would calculate the reaction quotient looks like this. And just at first glance, this looks suspiciously like that equilibrium constant. Well, it's because it's pretty much the same formulas. But the difference is what we're calling it. So here we're calling it the quotient to let our reader know that we recognize that this is not a reaction that is now at equilibrium. It's somewhere in the process and we're not sure. So if we look at this, we have our products. In this case, we're looking at the concentration. So we have the concentration of our products raised to their powers, or raised to their coefficients, and the reactants raised to their coefficients. Or if we have that information, we could use the partial pressures of the products raised to their powers, and the partial pressure of the reactants raised to their powers. So the big difference is how we communicate what it is that we're calculating. And the Q lets our reader know that we're coming up with a reaction quotient and not the equilibrium constant. So what are these numbers telling us? Well, in order for us to be able to know what these numbers are telling us, we have to have some idea of what the equilibrium constant is, because it's going to be a comparison. So let's take a look at what these numbers could be telling us. Let's look at that on the next slide. So what is all of this telling us? Well, if our quotient is greater than our constant, then the reaction is going to move in the reverse direction, and we're going to see the increase in the reactants and a decrease in the amount of product that we have. And then the opposite would be true. If the quotient is less than the constant, what we would see is the reaction moving forward, and we'd see a decrease in the reactants, but an increase in the products. Now there's still a couple more possibilities here. What if our quotient is equal to K? Well, then we have just managed to catch it at that magical moment when everything is in equilibrium. And what if our quotient is equal to 0? Well, then it means that we have a mixture that's just nothing but reactants, and this means that it's going to move forward in the forward direction, and we're going to see the creation of the products. And then there's still one more possibility. What if our quotient is equal to infinity? Well, then our mixture contains just products, and that means the reaction is going to start to move in the reverse direction. So this is how we're going to take our quotient that we have and our constant that we've been given, or maybe even calculated previously, and do the compare and contrast and figure out where we are with our current reaction. So we're at the point in this chapter where we can actually find an equilibrium concentration given the equilibrium constant and some initial concentrations or pressures. And we're going to use the ICE table in order to do that. So one of the things that we need to be able to do is, first of all, decide which direction the reaction will proceed. So if we're given our K, then it's up to us to calculate the Q, which we can do if we're given some concentrations or partial pressures. And we have to use the ICE table to do that. So that means that we're going to have to define the changes of the materials involved, our reactants and our products, in terms of X, and then use the coefficient from the equation as the coefficient for X in our ICE table. and making sure that X is positive for materials on the side of the reaction where it's proceeding to, so where it's going to. So it's not necessarily reading from left to right. It could be going from right to left, because remember, these are reversible reactions, which means that then X has to be negative for the materials on the side of the reaction where it's going away from. So if we are having a reaction that is moving from reactants to products, then our reactants would be decreasing, which would give them a negative number, and our products would be increasing, which would be positive. However, if our reaction was going in reverse, then our products would be losing, so we'd be losing products, make their values negative in the coefficients, and the reactants would be positive. And then we're going to solve for X, and we're going to use that quadratic equation to do that. So let's see what else we have to address here before we actually work a problem. Now we've looked at this ICE table before, and you might remember that the ICE stands for the initial amounts, the change in those amounts as the reaction proceeds, and then the equilibrium constant. And so what you're going to have across the top is you're going to have the concentrations of your products and reactants, and then you're going to have any amounts that you're given, usually the initial amounts, and then you'll figure out if there's something at equilibrium or if you're given a change, and then you'll be able to fill in the rest of this. So let's take a look at a problem. So we're being asked to consider the reaction between dinitrogen tetraoxide and nitrogen dioxide. And if we read through, we have one concentration value given right here for nitrogen dioxide. And we're being asked to find the equilibrium concentrations at this particular temperature right there. Oh, and we're given the equilibrium constant when we have the concentrations. For the concentrations. All right, so what is the first thing we're going to do? Well, we're going to use the balanced equation, there it is right there, and prepare our ICE table. So here's our ICE table, and we're going to plug in our two substances, our reactants and our products. Now we're only given one initial value, and that is for nitrogen dioxide, which means that we are at 0 for dinitrogen tetraoxide. So at this point we have completed everything that we can for this table. Now step 2 would have us calculate the reaction quotient for what we have going on. So we're taking that snippet of time, right here, the snippet of time where we have all nitrogen dioxide, no dinitrogen tetraoxide, and we're going to calculate what our Q is and compare it to our K. So in order to do that, we're going to be using this equation right here, where nitrogen dioxide is considered our products because it's on the right side of the transformation arrows, and dinitrogen tetraoxide is the reactant, it's on the left side of the arrow. And if we plug in the values, here's our value for nitrogen dioxide, and we're going to square it because we have two of them. You have to remember those coefficients, raising it to the coefficient. And we have 0 because we have nothing for dinitrogen tetraoxide. And when we do this math, we're going to get that our reaction quotient is equal to infinity. Now we know something about this, don't we? We know that when the reaction quotient is greater than K, that our reaction is going to proceed to the left. Now let's think about this for a second. What we're being told is that the only thing that we have currently is this, nitrogen dioxide. What can nitrogen dioxide make? Well, if in the reverse direction, it will make dinitrogen tetraoxide. So if all we have is nitrogen dioxide, then it should make sense that this reaction is going to move to the left and unmake the products and remake the reactants. All right, step 3 says that we're going to represent the change in concentration with regards to X. So what that means for us is that we know that there is going to be a loss of nitrogen dioxide and a gain of dinitrogen tetraoxide because this reaction is proceeding to the left. And the way that we would write that is first off like this. So we would have a negative X, but we have to have a 2 in front because we have a 2 right here. And then we would represent the gain here for dinitrogen tetraoxide like so. All right, now what? Now we need to sum each column for the reactant and each for the product and come up with some algebraic relationships with X. So let's do that. So now we're going to add 0. We're going to add 0 and positive X. That's good. And then we're going to add 0.1 and subtract negative, or we're going to subtract 2x. So now we have these two values to move forward. It's starting to look like something we can use our quadratic equation with, doesn't it? Okay, now we're going to substitute the expressions that we came up with for the equilibrium concentrations into the expression for the equilibrium constant, and we're going to use the quadratic equation for that. So here we have our reaction, and now we have some new concentrations or some ending concentrations for each of our concentrations. So here is from our table for nitrogen dioxide, here is our concentration, and for dinitrogen tetraoxide, here is our concentration. And these came directly from our table. Now, if we plug in the value, the given value of our equilibrium constant, now we can go somewhere. All right, so what we need to do is we need to be able to put this in quadratic equation form, which means we need to do a few things. We need to move this value to the right side of the equations, the equal sign, and then as we see over here, we're going to have to isolate x. So let's do this in a few steps. So the first thing we're going to do is we're going to multiply by x, everything by x, which means that we'll get rid of it in the denominator here, but it ends up showing up over here. And now we can move this value to the right of the equal sign. And by doing that, we've basically just flipped it around. So now we have a 0 on one side of the equal sign. And if we look at what we've done, we'll have to subtract 0.36 from this side, which means we have to subtract it right here as well. And when we do that, we're going to end up with 0.76, a negative 0.76, which we have right here. And here is our plus 4x squared. And then here is our positive 0.01. So we've done all of the steps that make sense in order to get 0 on one side of the equation sign and all of our terms on the other side, except that in this step we reversed it so that it looks a lot like this right here. All right, now we can isolate x using this formula right here. So what this means then is that we have to look at our 4 as our value of A, our 0.76 as our value of B, and 0.01 as our value for C, and we'll plug those values in right there. So there's our equation we're going to use, and here we go. So here's our B, it's a negative, and it goes into the equation as a negative, and it repeats here. And then we multiply 4AC. So 4A, A, C, and C. And then 2A. So here's our 2, 4 is our A. And now we do the math. And when we do that, we can, in one scenario, we will subtract, and in one scenario, we will add. And that's going to give us two possible values for x. So x can be equal to 0.176, or x can be equal to 0.014. Okay, now with our two values of x, we're going to substitute x into the expression for the equilibrium concentrations, those values that we calculated with our ICE table, and see what we get. Now when we do that, we're going to reject one of the values of x. We're going to reject the value of x equal to 0.176 because when we plug it in, it's going to give us a negative concentration for nitrogen dioxide. So we're not going to use this value. It's erroneous. It doesn't mean anything to us. But if we use the other value of x, we actually get concentrations that make sense in the real world. So for example, here we have our concentration value that we calculated with our ICE table. If we use 0.014 right here, here's our equation, and we end up with 0.072 moles per liter for our concentration of nitrogen dioxide. Now if we do the same thing for dinitrogen tetraoxide, we can see what its value is. So now we've calculated, using the ICE table and our understanding of the relationship of these variables, using the quadratic equation, to come up with these concentrations. So now we want to check our answer by substituting the calculated equilibrium values, these values, into the equilibrium expression and then comparing it to the given equilibrium constant K. So let's do that. So here is our equation, and we're going to take the value that we came up with for nitrogen dioxide, and we're going to square it. And then we're going to take the value that we came up for the concentration of dinitrogen tetraoxide, put that in there. So our equation looks like this. And when we do the math, we can see that our value of K, as we calculate it, our value of our equilibrium constant comes up to 0.37. Well, the given value ends up being 0.36. And since our calculated value is really close to the given value, we're going to consider that the answer valid. So it doesn't have to be precise, but it has to be pretty close. If we came up with something that was like 3.9 or 0.4, we might start to think that we were out of the ballpark on it. But the difference between 0.36 and 0.37 is valid. Now we've talked about a lot already that once a reaction is at equilibrium, the concentrations of the reactants and the products are always going to remain the same. Now, what happens if you disturb it? Well, if the conditions are changed, then the concentrations of all the players are going to change until equilibrium is once again restored. So this is a principle that was demonstrated by Le Chatelier. Furthermore, the new concentrations may be different in our new equilibrium, but the equilibrium constant, which tells us about the proportionality of the products and the reactants, will remain the same unless we change some other dynamic at work in the system, such as temperature. So Le Chatelier's principle guides us in predicting the effects that changes can have on the position of equilibrium in a system that is in equilibrium. So he was playing around with figuring out, well, I've got a system in equilibrium, and what happens if I add more reactant? Well, what happens if I remove reactant? What happens if I add more product? So he was seeing what was happening in those scenarios. There were other variables that he could have played with, such as volume, temperature, pressure that the system was at, in addition to the concentrations of the products and the reactants, and he did all of that. And he basically found that a system has a tendency to minimize a disturbance. Once it's at equilibrium, a system will have a tendency to adjust so that it minimizes the disturbance to that equilibrium. In order to understand what Le Chatelier was trying to demonstrate, we have to look at disturbing systems that are in equilibrium. So what if we were to do something like add a reactant? Well, if you add a reactant, you have to make sure, first of all, it's not a solid or a liquid, because otherwise the moles won't count. And if you do add additional moles of a gas, then you have to do a new calculation for an equilibrium constant, because remember, it's the ratio between the concentration of the products and the concentration of the reactants. And that's all easy enough to do. We know how to do that. But we need to ask ourselves a question. How will this affect the rate of the forward reaction? Well, adding the reactant initially is going to increase the rate of the forward reaction, but it will have no initial effect on the rate of the reverse reaction. The reaction then will proceed to the right until the equilibrium is restored. So what we're saying then is if we have a system that's currently in equilibrium and we add more reactant to it, what we're going to see is our rate of forward reaction moving forward is going to increase, but not necessarily see a decrease in the reverse reaction. So another important question to ask is, how will this affect the rate of the reverse reaction? Well, at the new equilibrium position, you will have more products than before, less of the non-added reactants than before, and less of the added reactant. But you won't have as little of the added reactant as you had before the addition. So let's actually see what we're talking about there. So at the point where you have added your reactant, your new reactant, you will now have this equation. So you have the added reactant plus the reactant that was already there, and we have now shifted the equilibrium to the right and we're making more product. So at that moment where we've added this and we've allowed some of the product to be made, at the new equilibrium, what we're going to actually see happening is, first of all, the establishment of a new equilibrium. And what we're going to see in our container is that we'll have more product than we had before. But some of the initial reactant that we had will get used, so there'll be a little bit less of that. And some of the added reactant will also be used, so there'll be less of that. So that's really what we're saying here, is that now we're looking at the concentrations. Together, the ratios will be the same as what we know the given was for the equilibrium constant, but the concentrations of the stuff that we're using to get there is going to be a little bit different, because now we have to include this player here. Technically, it would all be included here, but we would have its source being what we added. Now, the third question we need to ask is all of this that's changing, will that affect the value of our equilibrium constant? Well, the new equilibrium position, the concentrations of the reactants and the products are going to be such that the value of the equilibrium constant will be the same, as it should be, because remember, it's a ratio. So let's put all of this together. So let's say that we have our reaction that is at equilibrium, and let's assign some values. Let's say that we have 4 moles per liter of the reactant. We have the same for the product. This is not always going to be the same when we have something at equilibrium. It doesn't always mean that the amount of reactant will equal the amount of product. I'm doing it here just for simplicity's sake. So with these concentrations, we can calculate the equilibrium constant. So our equilibrium constant would be the amount of the product over the amount of the reactants, or the concentration of the product over the concentration of the reactant, and we can see that it would be equal to 1 in this case. All right, well, that's great. So let's say that we were going to add the reactant. And let's say that we added 4 moles of reactant. Now we know that initially that it's going to shove the arrow right, going to make the equation go towards the right, and that is going to increase the amount of product that we have. Now we're not given any values at this point, but if we were, another thing that we could calculate is the quotient. Given the concentrations at any given moment, and we could predict whether our equation was going to continue to the right or whether it was going to start to reverse and go to the left. But we're not given those values, so let's not worry about that. What we do know is that this equation at some point is going to reestablish an equilibrium, and we're going to have different values for the amount of reactant that we have and the amount of product. So let's say that instead of having 4 moles per liter of our product, let's say that we're going to have a little bit more product now, because we've pushed the equation to the right, and now at our equilibrium we're going to have 4 moles per liter of product. We're going to have a little bit less of the original amount of reactant that we started with. So let's say that we end up using a mole of that. Now we only have 3 moles of our original reactant. And let's say that we also consume some of the moles of the added reactant, so that we're down to 3 moles of that as well. Well, if we look at all of our concentrations, we have 6 moles per liter on the right of the transformation arrow, and we also have 6 on the left. So you can see why I'm keeping my numbers simple. So we could calculate this new concentration, this new equilibrium constant, and it would be 6 moles of product over 6 moles of reactant, and we would still have the same value, which would be 1. So that's how putting all of this together would work. So as we've seen, adding a reactant will decrease the amounts of the other reactants, and it will increase the amount of the products until a new position of equilibrium is found with the same equilibrium constant. Now, removing a product will increase the amounts of the other products, and it will decrease the amounts of the reactants. So hopefully that makes a little bit of sense. So overall, we can conclude then that equilibrium shifts away from the side with the added chemicals or towards the side with the chemicals removed. So remember, adding more of a solid or liquid does not change its concentration. Therefore, it's not going to actually have an effect on the equilibrium. We're only looking at the gases. So adding a gaseous reactant is going to increase its partial pressure, causing the equilibrium to shift to the right. Now, increasing its partial pressure will also increase its concentration, but it doesn't increase the partial pressure of the other gases in the mixture. Now, what if we added an inert gas to the mix? Well, it's not going to have any effect on the position of equilibrium because it doesn't affect the partial pressures of the other gases in the reaction. So an inert gas has no effect, kind of like a liquid or a solid. So there are other variables that we could shift around in these scenarios, and one of them is volume. So what if we decrease the volume of the container? Well, decreasing the volume of the container will actually increase the concentration of the gases in the container. Because remember, gases are moles per volume. And that means it's going to increase their partial pressures. Now, that's only the effect of gases. It's not going to change concentrations of solutions that may also be in that container. Now, if the partial pressures of the gases increases, then the total pressure of the container will increase. And according to Le Chatelier's principle, the equilibrium should then shift to remove that pressure. Because, you know, Mother Nature, she's kind of lazy and she likes things to be low maintenance. And the way the system is going to reduce that pressure is to reduce the number of gas molecules in the container. So that when the volume decreases then, the equilibrium will shift to the side with the fewer gas molecules. In the scenario where we have an equilibrium established, let's say that we change the container volume, let's say we decrease it. Our questions become, how will this affect the concentration of the solids, the liquids, the solutions, and the gases? How will this change in volume affect the total pressure of the solids, liquids, and gases? And will it affect the value of our equilibrium constant? Well, decreasing the container volume will increase the total pressure. That's Boyle's law. As pressure goes up, volume goes down. As volume goes up, pressure goes down. So there's an inverse relationship. And if the total pressure increases, then the partial pressures of all the gases will increase. That's part of Dalton's law of partial pressures. Now, because the total pressure increases, the position of the equilibrium will shift to decrease that pressure by removing gas molecules. So that means it's going to shift to the side with the fewer gas molecules. And at this new equilibrium position, the partial pressures of the gaseous reactants and products will be such that the value of the equilibrium constant remains the same. So that's what happens. Well, we have another variable we could consider, and that would be that of temperature. And Le Chatelier's principle does ring in on this as well. And in this scenario, it looks at heat as like part of the, in an exothermic reaction, it looks at it as part of the products. It's not really a product, but that's where it gets written in an equation. So we can think of an exothermic reaction, it's one that releases heat, and because of that, we could think of the heat being as part of the products. And we would say that heat is acting as a product, and that increasing the temperature is very much like adding heat to the equation. And according to Le Chatelier's principle, the equilibrium in this scenario in an exothermic reaction would actually shift away from the added heat. So here we have an exothermic reaction in equilibrium, and let's assign some values because I want to calculate the equilibrium constant for this. So if we were to take the the concentration of the products right there, and put it over the concentration of the reactants right there, we could get an equilibrium constant of 1.5 for this exothermic reaction in equilibrium. Even though we know that heat is over here, we're not going to worry with it because it doesn't go into our calculation. But if we do add heat to the product side, we know that it's going to cause a shift to the left in this equilibrium. So by adding heat to the exothermic reaction, what's going to end up happening is we're going to decrease the concentration of products because some of our products are going to be turned into reactants, and we're going to see an increase in the concentration of reactants because we got the conversion of the products. So let's assign some new numbers after having added the heat. So let's say that we used up 3 moles of our product, leaving us with 3 moles, and those 3 moles went over to our reactant. So now we have 7 moles of reactant. If we calculate a new concentration constant, we're going to see something very different. Now we're going to see that the concentration constant went down quite a bit because of the loss of the products. So from this we can then conclude that by adding heat to an exothermic reaction, it's going to decrease the value of K as a result of having lost some of the product and having seen a gain in the concentration of the reactants. So here we have our endothermic reaction, and let's go ahead and assign some values so we can calculate an equilibrium constant. So let's say we start off with a total of 6 moles per liter of reactants, and we also have 4 moles per liter of products. And we can plug those values into our equilibrium constant formula and actually get a number. So at the beginning of this, we have an equilibrium constant that is 0.67. Now, what happens if we add some of this heat in here? Well, we know that adding heat to an endothermic reaction is going to decrease the concentration of the reactants, and it's going to increase the concentration of the products because this reaction is now being driven to the right. It is favoring the production of the products. So what we'll see is a loss of our reactants because they're being converted to products. So we'll see that gain in our products. Now, if we take these values and do a calculation for a new equilibrium constant, we can see then that our equilibrium constant has shifted quite a bit and has gotten significantly bigger. And Le Chatelier's principle does predict that. So by adding heat to an endothermic reaction, we're actually going to see an increase in the value of our equilibrium constant. So to summarize this concept of tweaking the temperature and its effect on equilibrium, in an exothermic reaction, we're going to think of heat as part of the products. And if we increase the temperature, that's going to cause this exothermic reaction to shift to the left, because remember, heat is a product, it's going to be on the right. And as a result of this shift to the left, the equilibrium constant is going to decrease. Now, what happens if we decrease the temperature? Well, it's the same thing as pulling out products. And that means that it is going to create a shift to the right. And we're going to see the value of the equilibrium constant increase as a result of that. Now, the opposite is true in endothermic reactions. In the endothermic equation, we're going to think of heat as a reactant. And when we increase the temperature, in an endothermic reaction, we're going to see a shift to the right. So it's going to favor the production of products. So we're going to see more of our reactants moving into the products. And as a result of that, we're going to see a decrease in the equilibrium constant. If we decrease temperature in an endothermic reaction, it's going to shift to the left. It's the same thing as pulling out reactants. The equilibrium constant, therefore, will decrease. Now, we've talked a little bit about catalyst. What is the effect of a catalyst on equilibrium? Well, catalysts are going to provide an alternative, more efficient mechanism, and they're going to work in both forward reactions and reverse reactions. Catalysts affect only the rate that the reaction occurs, and therefore catalysts do not affect the position of the equilibrium. They only affect how quickly you get there. Because think of this, remember, our equilibrium is based upon either partial pressures of gases or the concentration of our gaseous products and our gaseous reactants. And catalysts do not participate in either one of those arenas. They're not part of concentrations or they're not part of partial pressures. So therefore, they don't affect anything. And with that, we are done with Chapter 15.